All right, good morning, everybody. Today is the 4th of October, and we are talking about moments of inertia, and we are going to start reviewing the parallel axis theorem. But the important points that we need to know at this time, for this class, we are not going to go back to the integral form of the moment of inertia. All we're going to use are composite shapes. And the moments of inertia about the neutral axis or the centroid of an object is always found using composite shapes and the parallel axis theorem, which is what I'm going to talk about right now. So the parallel axis theorem tells me two things, and I'm introducing this without proof. You may have had proof of this when you were in statics, but I'm just introducing this functionally right now. One is the moment of inertia of any shape is the smallest about the neutral axis or the centroid. And those two things correspond. The centroid is more of a mathematical concept. The neutral axis is more of a mechanics and materials engineering concept, but they correspond in these cases. And the second part of the parallel axis theorem is the moment of inertia about a parallel axis, and when I say parallel, I mean to the centroidal axis, is given by this formula. The moment of inertia about some random x-axis is equal to the moment of inertia of that shape about its centroidal axis plus the area of the entire shape times d squared, where d is the distance from the centroid of a piece, whatever piece it is, to the centroidal axis of the entire shape. And I will show you what I mean. All right, so let's go back to a simple rectangle. I'm going to do this very quickly. And if we have a height and a base, if I look at the shapes, because we're not going to use the integral form, if I look at the shapes in the back cover of my book for a rectangle, I will see that Ix bar, or if I look at that x prime, this is actually kind of redundant. If you look at this, it says I with a bar above it, which means centroidal, and then it says x prime, and if you look at the picture, you can see that x prime is the centroidal axis. So it's really saying that two different times. It's saying the centroidal moment about the centroidal axis, which is redundant. But it's saying that the moment of inertia about the x bar axis, or x prime axis, is 1/12 base height third. It also says that the moment of inertia, not about the centroidal axis, but about the x-axis, which is at the base of this rectangle, is 1/3 base height to the third. So let's see if that makes sense or if that works with our theory. So the parallel axis tells me if I accept that the centroidal axis is 1/12 times the base times the height to the third, and I want to know what it is about the base, parallel axis theorem says I would add the area, which is the height times the base, times the distance from here to the centroidal axis, which is 1/2 times height. And it's this distance squared, okay? Because this distance from the axis I'm going to, it's not the centroid of the piece, from the axis, from the x-axis in this case, phrase better. Okay, so this distance, if the entire height is h, this is going to be 1/2 h. So here's my distance squared times h times b. Ix equals 1/12 base height to the third plus, if I square this, I have 1/4 height squared times height to the third, or height is height to the third, and base. And if I take this and I multiply it by 3 to get a common denominator, I get 3 plus 1, or 4/12 base height to the third, which reduces to 1/3 base height to the third is the moment of inertia about the base. And if I look at my book, that's what it tells me. So that's not really a mathematical proof, but it's sort of an engineering problem that illuminates the issue that the parallel axis theorem works. Now, the one thing that I want you to notice is that Ix bar, this always must be centroidal, must be a centroidal moment of inertia. In other words, the smallest value that it can be. All right. You can't do this between two random axes. You can only do it between a centroidal axis and another non-centroidal axis. All right. Well, let's take a case where we have a shape that we need to do something like this to find the moment of inertia of a particular shape. And I'm going to start with something where I know where the centroid is, and then I'm going to do one where I don't know where the centroid is. So I assigned problem 2 and problem 9. Is that correct? Yeah. Okay. So I'm going to do problem number 3 to begin with, 4.3. I'm not going to do the entire problem. I'm just going to find the moment of inertia. And then I'm going to, because I can tell by symmetry where the centroid is, just like for problem 2. Okay, problem 4.3. The cross section looks like this. And this is called the web and this is called the flange, but it's also the shape of an I-beam. We're told that this dimension is 200 millimeters. We're told that this dimension is 12 millimeters. We are told that the bottom is the same. So this is 200 millimeters. And this is 12 millimeters. This is 8 millimeters. And the entire height from top to bottom is 220 millimeters. Okay? And I'm just going to read the question to you. It says, using the allowable stress of 155 MPa, determine the largest bending moment M that can be applied to the wide flange beam shown. Neglect the effect of the fillets. Okay, so in other words, we're just viewing this as being 3 rectangles. We're not taking into account that there's any curvature. It's also not a particular rolled steel shape where we can pull the moment of inertia off the tables in the book. We have to compute the moment of inertia based on this shape. All right, so I know that sigma is equal to, or let's say sigma max is equal to my over I. And I know this. I can find this. Now, if you look at this, this is symmetric, 212, 212, and then I have the web in the middle. That is also symmetric. So by symmetry, if I were to fold this over on a line, I would find that the neutral axis is right in the middle because the top part will fold right over the bottom part if I fold it in that way. So by symmetry, I can see where the neutral axis is. Okay? So I have everything I need except for I x bar equals what? Well, the answer to it is I have to look at this as a composite shape. I'm going to get a better piece of paper here. Hang on.
Is that sigma equation, is it negative in y?
Yeah, it is. Thank you. It certainly is. Okay, let me see, get this on here. Hang on. Okay, there we go. All right, so what is my IX bar? Well, the answer is I have to look at this. I can look at it in two different ways. I can look at it as the top part, the middle part, and the bottom part. Or I can look at it as the entire thing, a rectangle, in that whole thing. So I can look at this plus this plus this, or this minus two cutouts on the side. It does not matter which way I look at it. It just depends on what is easier for you to see. The advantage to this one is I wouldn't really have to use the parallel axis theorem. So I'm going to go ahead and do this one because I really want to show you guys how to use the parallel axis theorem. So why don't you have to use the parallel axis theorem here? Well, the reason is because the cutouts, if I look at it that way, have the same neutral axis. In other words, the central axis is at the same y value as it is for the composite shape, or for the big rectangle. But here, my centroids are going to be different. My centroid here is going to be halfway through this rectangle. My centroid here is going to be halfway through this rectangle. My centroid here is going to be the same as the neutral axis for the entire shape. But so I'm going to have to use the parallel axis theorem for this and this. All right, so I sub x then. Now the other thing to remember is moments of inertia are always positive. When we have to find first moment, which we have to do one if we have time today, or else we'll do it on Friday. But when we find something that has a non-symmetric shape, we first have to know where the neutral axis is. And that, in order to do that, we have to use a first moment, which is that q equals the integral of y dA, if you remember from statics. And because y is not squared, dA, if it's a positive area, has to be positive, but y can be negative or positive, so the first moment can be negative or positive. If you look at the original formula for a moment of inertia, it's always positive because it's y squared dA. It's always positive unless you have a negative area, then you subtract it. But what that basically means is that if I take this, as I told you, one of the things about a moment of inertia, one of the things it represents is a resistance to bending or a resistance to turning. So if I take this and I spin it about its neutral axis, it's easier to spin. If I spin it about any other axis, whether it's on this side or this side, it takes more of a oomph to get it to spin, and the spin is less regular, isn't it? That's because the moment of inertia is higher about any axis except the centroid. So you get the smoothest spin when you're at the centroid, and you get the lumpier spin when you're not at the centroid, and the direction doesn't matter. It's just bigger. Okay, because that's y squared. That is y squared in being demonstrated by this high-tech ruler right here. So there you go. So in order to find I sub x, we have to do, I'm going to call this the top. These are called webs, and this is called the flange, or the other way around. But I think it's this way. It may be web. So it's going to equal the I of the top web plus the I of the flange plus the I of the bottom web. So I sub f is easy because the flange has the same neutral axis as the entire shape. So this is just 1/12 times the base of the flange, which is 8 millimeters, times millimeters, times the height, which if this entire thing is 220, this is 12 and this is 12, that means it's 220 minus 12 times 2, or 24, which is 176 millimeters, isn't it? So 176 millimeters to the third power. Now, due to symmetry, if I do this, okay, if I take, let's just do the top, and I'll show you what I'm going to do. The top web I did that backward. This is called the flange, and this is the web. Sorry.
Isn't our long distance is 220?
Yes.
So we should
Oh, it's 220. Thank you very much. That's 196, isn't it? Did I do it right that time? Okay. Yes, whenever I do that, that's just a mistake. So I appreciate you pointing it out. It's not a, like I said, I've heard some teachers say they do that to see if people are staying awake. I make enough mistakes on my own. I don't need to try to see if anyone's awake or not. The person who needs to be awake is me, I guess. Anyway, so if I look at the top, if I use the parallel axis theorem, I can say that because what I want to do is I want to move it from here, the centroid of this piece, down to the centroid of the entire object. So it's going to be 1/12 times the base, which is 200 millimeters, times the height just of that top flange, 12 to the third power. Then I need to add plus the area times the distance from here to here squared. Well, this is 6 millimeters down, right? If this entire distance is 220, I know that if I think about starting from the top, this distance from the neutral axis here to the very top would be half of that, or 110, but my neutral axis, the top piece, is halfway down at 12, or minus 6. So the distance from the neutral axis of the top piece to the neutral axis of the entire object is 110 minus 6, or 104, once again in millimeters squared. So here I've used the parallel axis theorem to find out the moment of inertia of this top piece about the neutral axis of the entire object. Now, what do you think, before I do that math, what do you think about the bottom? How do you think the I of the bottom piece is going to compare to I of the top piece? It's going to be exactly the same. That's right. So bottom equals same. All right. So, and I've left this in millimeters on my paper. I'm going to probably just go ahead and do that and get these huge numbers. So the middle part here, we have 196 raised to the third power multiplied by 8 divided by 12. So the piece that I contributed by the middle part is 5,019,690 millimeters to the fourth. The top piece, the contribution from the top piece, is going to be 12 raised to the third power times that width, which is 200, divided by 12. So this piece of it, I sub x, the I sub x bar piece of the top is 28,800. And then the AD squared piece, this is 104. $12 times 200. 2,595,8,400. 25,954,000. Yep. So the bottom is the sum of those two numbers, or the top is the sum of those two numbers, 28,800. And that's, so each one of those pieces is 2,598,7,200. That's in millimeters to the fourth. And so if I multiply that by 2, because the top and the bottom are the same, um, 5,197,400 millimeters to the fourth. Okay, so I have 51,974,400 millimeters to the fourth from the flanges. And if I add to that the piece from the web, 5, 0.019, 690. I get a total of I sub x about that neutral axis of the entire thing is 569949090. Yeah, that looks about right. 56 million millimeters to the fourth. Okay, now I've shown you the work. You can also probably see why you don't want to keep this in millimeters to the fourth, right? Because that's a mess, is what that is. If you change it to, because if you think about it, there are 1,000 millimeters in 1 meter, or that is 10 to the third millimeter equal 1 meter. So if you take millimeters to the fourth power, let's do it this way, times 1, let's say 10 to the third millimeters per 1 meter, and if you raise this to the fourth power, you get 10 to the 12th on the bottom. So you get this number times 10 to the minus 8, which would be 5.02 times 10. That would be minus 6 squared, minus squared meters to the fourth. So that's a more manageable number. Okay. Anyway, but I hate to do this. Taking units to higher powers always messes people up a lot more than it should. So I prefer to just go to base units right at the beginning. All right, so that's how you use the parallel axis theorem if you have enough symmetry to see where the neutral axis is to begin. What if there is not enough symmetry to see where the neutral axis is? And having said that, you guys are doing problem 4.9, which is one that you cannot see where the neutral axis is to begin with. And I will do problem 4.11, because we have to find the neutral axis. On problem 4.11, we have a cross-section that looks like this. It's a U-channel. Okay. And the thing is if this were a box beam like this, we would have enough symmetry that the neutral axis would go right through the middle, right? But we don't have a top piece here, so we don't know where the neutral axis is. So the way we do it then, I would divide it up into 3 pieces like this. And the first thing we have to do is to determine the neutral axis. Well, the answer to that is the neutral axis is at the centroid. And if you recall, the theory tells us the first moment of inertia, or Q, which is equal to the integral of y dA, is equal to 0 at the centroid. So what we want to do then is to find Q for this composite shape and find where it's equal to 0, and at that point that will identify the neutral axis. And this should be a review, but I don't know if it is or not, so that's why we're doing this. All right, so what I like to do, and this is right from your statics book in chapter 5, I break this down into all of the pieces that go into the shape. And that would be shape 1, shape 2, shape 3. Looking back at the integral, I choose a y value. Y value is, I choose a location, an origin. I call this 0. Usually I like the lower left-hand corner, but there's no reason to that. Y, which will be in, let me see my units, millimeters, is the distance from this point to the centroid of that shape. Okay, it's a distance. Then I compute the area of each of those shapes by multiplying, in this case, the base times a half. Then I find the little piece of Q, which is yi times ai. In other words, the individual y value times the individual I value. And then what I do is I find the area, the summation of those individual areas, the summation of the individual YI values, and then I say, therefore, that y bar, which is the distance from my origin to the centroid, or the neutral axis in this case, is equal to the summation of these things over the summation of these things. So you can always do it this way. We're always going to have simple shapes. They're not going to be big deal shapes. You just have to remember we're talking about distances from a point. So you have to choose that point and then stick with it. All right. So if we take a look at this, the way I have it drawn, shape 1 begins right here, and that measurement is 10 millimeters from the top, from the bottom, and then the entire thing from there to there, from here to here, is 50 millimeters. So if I look at piece 1, the distance, the centroid of this is right in the middle, so it's 25 millimeters from here, which is 10 millimeters from here. So it's 25 plus 10, or 35 millimeters. Same for piece 2. Part 3, on the other hand, is this is only 10 millimeters high, so this is only 5 millimeters from my origin. The area of 1 is 50 times 10, or 500, and similarly for 2. And the bottom piece, the way I have it drawn, this is 50 across, 50 times 10, it's also 500. Okay? So I have 35 times 500 is 17,500. And then 500 times 5 is 2,500. So I add those three numbers together. And I get 37,500. And you can see this is going to be in millimeters to the third. It's going to be a millimeter squared. When I add my areas together, I get 500 plus 500 plus 500, which is 1,500 millimeters squared. So millimeters to the third over millimeters squared. So this value is going to be in millimeters. So I take 37,500, divide it by the sum of the areas, which is 1,500, and I get 25 millimeters. That means that the centroid of this object is 25 millimeters from the bottom. The entire thing is 60 millimeters high because it's 10 plus 50. So what this piece has done essentially is lowered my neutral axis by 10 millimeters. Does that seem logical to you? Does that seem like that would be a good balance point? It kind of does, doesn't it? Because this is going to be kind of clocking it downward if I were to try to balance it. So it makes sense that the neutral axis would drop down a little bit. Do you have a question, Jess?
You said the length in pieces 1 and 2, like the height.
Yes.
Was,
oh, yeah.
did you say it was 15 or 25?
It's 50 right here.
50? Oh.
50,
Okay.
and this is 10.
Gotcha.
So the distance from the bottom to the top is 60 millimeters. Okay.
So Y bar always from the bottom of your.
The Y bar, that is such a good question functionally. You have to choose a point, a location, a coordinate, and then always measure all of your Y bars from that point. You don't have to choose the lower left-hand corner. You could choose the upper left-hand corner, lower right, whatever you want. But I like to choose the left-hand corner on the lower side most of the time, just because it keeps it consistent. But for every one of those pieces, you have to always do Y bar from the same point. And then your neutral axis Y bar that you compute will also be from that same point. Does that make sense? Okay. Alrighty then. So now we know where the neutral axis is, and we only have 2 minutes left. But the deal is that none of these three pieces has the same neutral axis. So that means that in each case, my I about my new neutral axis is going to involve using the parallel axis theorem. So for parts 1 and 2, that means it's going to be 1/12 times the base of each of these upward pointing legs, 10 millimeters, times the height of each of those, raised to the third power, plus the area of each, times the distance from the centroid of each of these pieces to the neutral axis of the entire thing. All right, well, if you look at this shape right here, 1 and 2, they're 50 millimeters tall, so it's going to be 25 millimeters up into this, but there's 10 here, so it's going to be 25 plus 10, which is at a location of 35. My neutral axis is at 25, so my distance between those two, 35 minus 25, is 10. So there's that. Oops, sorry, times 2, not squared, because 1 and 2.
You just did.
Mhm.
That's from where?
I'm still keeping my 0 right here. Okay, so if you look at piece 1 and 2, let me redraw this. So it's a little bit bigger. Let's just look at piece 1. This distance is 50, right? So my neutral axis, or my centroid of this, is at 25 from here, right? But to go back to my 0 that I chose, this is 10. So that means that from my 0, it's 10 plus 25, which is 35. I computed using my Q's that my neutral axis of the whole thing is at 25 from here. So if this is at a coordinate of 35 millimeters from my 0, and this is at a coordinate of 25 millimeters from my 0, 35 minus 25 is 10. And that's the distance between the neutral axis of 1 and the neutral axis of the entire shape. Okay, so good? And 2, mercifully, is exactly the same. So we're not going to, we just multiply it by 2. All right, part 3, and I know I'm going fast. I'm doing this because I want to get it on the vodcast so that you'll have it. We're going to have to do the same thing. 1/12 times the base of part 3, which is 50 millimeters, times the height of part 3, which is 10 millimeters raised to the third power, plus the area, which is 10 times 50, times the distance, which is the centroid of part 3, which is 5 millimeters up, to the centroid of the entire thing, which is 25. So it's 25 minus 5, which is 20 millimeters squared. So if I take this quantity, multiply it by 2, add it to this, I will get I about the neutral axis for this unsymmetrical shape, or non-symmetrical shape. All right. Do you guys have any questions? All right. This is clearly the most difficult part of an unsymmetric cross-section. The rest of it is just my over I, you know. So, but finding I is the more difficult part, because first you have to find the neutral axis using the Q, composite Q. Then you have to find your I using parallel axis theorem for each element. But we won't use the integral. That's the good news. All right. All right, gentlemen. Well, that's it. I'm going to turn off my streaming. There we go.